Should we go on? Or? Okay. Okay, we're gonna go on with the second part of the tutorial. What? We're gonna go on with the second part of the tutorial. So, the next notebook is 6 model complexity. And so this might be a little bit much now, but you'll understand this better in the next notebook when we go through some of the models. So, I forgot to run the first cell, sorry. As I said before, what we really care about is making predictions on a new data point that we haven't seen before. And what's very important on how well we can make predictions on new data points is how complex a model we try to fit. So here I have like a regression model. I have some true function in blue, which is like a sinus function that's like rising. I have some samples from this function, which are like green points, with some added noise. And then I try to fit a regression model to this function, which you can see in red. Well, it's red on the screen at least. So the regression function model I used here is k nearest neighbors. It just looks at the 2 nearest neighbors of each point and takes their average as a prediction for you. So the 2 nearest neighbors in the training set. And you can see that gives you a very, very noisy estimate of the underlying function. If you consider more neighbors, so if you want to make a prediction and you look at the 5 nearest neighbors in the training data set, you get the picture in the middle, which is much more smooth and reflects the true function much better. If you consider even more neighbors, like take the average of the 20 nearest neighbors in the training set, you get an even smoother estimate, but now it's over smoothed and doesn't capture their underlying function very well anymore. So there's a concept of model complexity here that says how wiggly, how complex do I allow my machine learning model to be. So here, if I take a lot of neighbors, I'll have a very smooth prediction, but I might not capture the underlying structure really well. If I allow myself a lot of degrees of freedom, I'll have like a very complex model, like the one on the left, but I don't really capture the underlying concept. So if I try to predict on new data, I might not generalize very well. And this concept of model complexity exists basically in all machine learning models. And I have this cartoon graph here that illustrates what's happening. So here on the x-axis, I draw like how complex you want your model to be, allow your model to be. And on the y-axis, you have how well you do. And in blue, I show how well you do on the training set. So in the training set, the more complex a model you allow yourself, the better you can fit on your training set. And basically, if you allow an arbitrary complex model, you can fit your data set perfectly, and you do very well. However, if you look at how well it generalizes to new data, if you have too simple a model, you will not be able to capture the data. So you do bad on a training set, but also generalize very badly. If you allow yourself more complex a model, you'll get better. But if you allow yourself to have too complex a model, you'll fit the particular noise in the training set, and your model will be too specific to the training set, and what you learn will not generalize to new data anymore. And this is what you see on the right-hand side. This is called overfitting. And so there's usually some parameters in your model, like above we say like the number of neighbors we consider, and these parameters say how complex a model you want. And you want to adjust these parameters to find sort of a sweet spot where your model is complex enough, but not too complex. And so now we're going to go through some methods to analyze where the sweet spot lies, and methods to find this sweet spot. So After this, I'm going to go into details into the models, but now let's again use them as black boxes. So one method to actually draw this curve basically is a validation curve function in Scikit-Learn. It varies some parameter and gives you the training and the validation score, and uses cross-validation internally. So here I load this digits data set of the handwritten digits again, and I use the random forest classifier, and I set some parameter range here for there's like the range from 1 to 13, and this is for the parameter maximum depth, and I'll explain this on the next notebook. And so what the validation curve will do, it will do 5-fold cross-validation on this data set, x and y, the digits data set. And for each of these values of the maximum depth parameter, it will give me the training scores. So there's 12 different settings of the parameters. So it will give me 12 training scores, also gives me 12 test scores. And there's 5 for each of the 5 splits. So maybe I just show this one. So here, sort of each row corresponds to one setting of the parameters, and each column corresponds to one split in the cross-validation. Then I define a function that's just some matplotlib. It computes the mean and plots some pretty plots. And then you can, if I call a function, you can see here, for this parameter, the maximum depth, you can see the training score is rises if you allow greater maximum depth. So this is more higher values mean more complex models, and if it's very low, then you very bad. There's actually no overfitting here, so if you make the maximum depth very high, you don't get worse on the cross-validation score. But what's typical here is that sort of for very simple models, the training and the cross-validation score are very close, whereas here later they get further apart. And maybe you can use this validation curve function, a plot validation curve, for 2 more classifiers, for the linear support vector classifier that we saw before, with where you change the parameter c, and for the k-neighbors classifier, where you change the number of neighbors k. That's actually called n neighbors. So you can plot again the curve using the validation curve function and the plot validation curve to see how the model behavior changes when you change these parameters. The parameter c in the linear CC and the parameter n neighbors in the k-neighbors classifier. And afterwards, we're going to go into and explain what these parameters actually do. So quiet now. Yeah, I should have changed the order of the stuff a little bit, I think. And then the exercises wouldn't be as good. Not the reply.
I have absolutely no idea.
Why not?
Yeah. Because I don't know anything about these models. So.
Okay, but you know something about the k-neighbors classifier.
I suppose if I give it more than 10, it will behave badly, right?
Why?
Because there are 10 things that we should be breaking the data up into. So that's my first guess.
So,
right? So if I'm spreading across more than the number of points that there are, the number of objects that there are, then it should start to behave badly.
it doesn't, because the points that are close to each other are usually from the same class, right?
Sure.
So the question is sort of, so if you look at only one nearest neighbor, how would you think that would do on the training set? So you look at the closest neighbor in the training set and give it that label.
Right.
What would that do?
All phases, because backstep could exist for...
Yes.
Yeah, maximum.
Oh. So are we passing any parameters here in SVC?
Read the exercise description.
Oh, got it. So you can choose things and you want to say, not really want to
So
sure around
in the
or make
example,
it bigger or smaller.
Set that parameter. Can I see what you got? What change it was? Because I was not.
There was, I think, someone asked, what is this C?
Yeah.
I remember, and so when we, well, I can't because it's thinking right now. When we do linear SVC question mark, we'll see that there's a parameter C that what type of, what level of detail you're using.
But so what do we pass?
So the other one that they were using up here, which was
Why does that function take in a pre-constructed classifier object or estimator object?
What else should it?
The class name.
Because you might set other parameters.
But if you pass in an object, you might implicitly share state across cross-validation folds.
No.
That would be a bug, but it would be an easy bug to make, right?
But calling fit twice never changes. Calling fit erases all state.
And that's guaranteed?
That's guaranteed.
Okay. Yeah, I still don't like it. It's depending on
what
guaranteed be held.
Yes, but wait, how would you put in, how would you otherwise put in a model?
Like grid search CV, so you just have a parameter.
Grid search CV.
You have a parameter that doesn't have multiple values, just a single one. Right, if you want to have fixed parameter values, just say like C:10 instead of
No, but
A range.
grid search CV takes a object, not a class.
That took a parameter dipped.
Yeah, but I thought you were talking about, I'm not sure. Okay, I'm not sure I understand.
I thought grid search CV took a... Well, I think that shouldn't take an object either. It should take a class.
No, but it can be a pipeline. So let's say it's a pipeline.
Right.
It's a pipeline. The first one is, and it uses a meta estimator to do recursive feature elimination.
I understand.
Number of estimator is the number of trees.
Yes, the number of trees.
Is the range of the parameter, what is this?
This is the maximum depth of each tree.
Okay, from 1 to 13. So
Yes.
how long was going to be the tree?
Yeah, how deep?
Okay. All right. We don't say anything about the number of features that each tree will have.
Yeah, you can adjust that too.
Okay, but
I'm
now
not doing
it's
it here.
gonna be-
Now it's gonna use square root of number of features for each split.
It's gonna what?
Square root of number of features. That's the default value.
Squared.
Yeah, square root.
Square root. Ah,
Yeah.
okay.
I was modifying that.
So your model would be linear SVC. Oh, and it needs parentheses.
If we're gonna, if the ambitious project for today would be to take do a bunch of what the angles and scale and offset and everything are for all those projections.
Oh, sorry. Yeah.
Make a model
Never mind, I'm dumb.
When I call this, there's a numpy call that's like convenient called log space.
And you can take a little bit less than 100.
Yeah, I take a lot. I just
Yeah.
do that. Sorry.
Because that's why you had to wait a bit.
Yeah. But anyways, so yeah.
Oh, and then instead of
that-
maxed up, you have C.
Yeah.
Is that for the SVC? No. This is
This is the linear SVC, yeah.
Oh,
But
very good.
it caused my computer to lock up, and now I can't do anything.
I'm sorry.
Just gonna wait it out. It'll come back, I'm sure.
But it's a nice graph.
Counts, right?
What is a good range?
Well, that looks good. I mean, now you know that the best range is there.
Yeah.
But just
Should I? Yeah, no, sorry. Should I be getting something that's flat?
no. Maybe if you want to extend your range a bit.
Okay. Okay, so
So
just because
what
I'm not
is the
looking at
issue?
them.
Yeah, so what is the issue?
Okay. Yeah, maybe things have changed. Yeah. Since then, it does move pretty fast. So. Yeah, I got it.
Do you need any help? Or okay.
I added noise and a bit darker, so maybe it's just not really. I haven't sampled a wide enough off of this range to see where it's either overfitting or
So you don't have to worry about that.
it doesn't matter if I plot over a larger range.
Try -5 and 5. Wait.
It'd be nice to wait that way.
No, it's logarithmic grid.
Plot space of 10 to minus
Okay,
5.
so I mean, I was just trying to get this test value.
In your universe classifier, what module is that?
Neighbors.
Yay!
Okay.
I got something that looks like a curve.
Well, look at that.
Question. The way that you showed this little diagram here, does Y always, does the thing you're mapping to, like your classification scheme or whatever, does it always have to be one-dimensional?
Most.
No?
Not always, no.
Okay.
But mostly yes.
Mostly.
Mostly yes.
So what do you want it to be?
Well, I was talking to someone who wants to do a thing, and it's sort of like a three-pronged, like you want to take input data and be able to predict 3 different properties.
I mean,
You're
so
not necessarily interested in classifying.
I mean, you can do the 3 independently, right? That you can always do. You can predict, but maybe they have some shared structure, so you want to do them at the same time. So, I mean, the first thing you try is do this independently, and then see if that works at all. But then some of the models allow you to share. All the tree-based models, yeah, okay, and allow you to use information for all the shared models. For all to make predictions for all 3 at once, and that might give you better predictions. So all the tree-based models allow you to do that.
Tree-based models. Okay.
And KNN also, but it's not going to be the results not going to be different from making individual predictions.
Okay, I think that answers my question now.
Yeah.
When you called the in-average cost, is there anything you put in?
And I kind of felt like, she said something under her breath that she did repeat them.
Cool.
Publicly admitting that I did.
What? Okay, so maybe let's go on. And so if you use like a large enough logarithmic grid over the parameter c, you can get something like this. So if you put in the plot validation curve also the logarithmic grid, it will look very bunched up. So I changed.
Wait. Can you announce when you're starting again so that those of us in the back?
I announced that I'm starting again. Okay, you can't hear? Okay, sorry. Maybe that works. Okay, great. It would be great if we could use that mic. But anyhow, okay, so if you use enough logarithmic grid over the parameter c, for the linear SVC you get something like this. So for so I changed the thing I plot against to be not the logarithmic grid, but just regular grids. Otherwise, it looks too bunched up. But what you can see is that for the small values of C, you are basically underfitting, and they're relatively close. Training in cross-validation score. If you allow C to grow, then you get a better cross-validation score, and then here you get some overfitting if you make it too big. So this basically looks exactly like the cartoon I showed here.
So the value of C there was like at the peak is like 10 to the minus 4 or so.
Yes.
What is that?
Oh yeah, the question is, the best possible value is 10 to the minus 4, or something around there. What is that telling me? So that tells you there's noise in the data. Because it's small. That means the data, so the model needs to be simple. So if there was basically, the more noise there's in the data, the more simple you need to keep your model. But it also depends a little bit on how you scale your data. So, but I wouldn't overinterpret this, but basically, if there was no overfitting, it means, or if there's little overfitting, it means there's little noise in your data. In particular, this is a linear model. Linear models are somewhat simple in a way. So if even the linear model is overfitting, it means there's probably a lot of noise.
It's a good job there's only one parameter to tune.
So yeah, we only tune one parameter at the moment, so we can plot it. Usually there's more than one parameter, and we're going to go into this in the next notebook. But then plotting is harder. So here, actually, for the k neighbors, it's a bit flat, but you can zoom in. So what? Maybe you can zoom in a bit more. So what you can see is that for one nearest neighbor, you actually have 100% accuracy, because each data point is its own nearest neighbor. So you're overfitting a lot if you only look at the nearest neighbor. And there's some sweet spot here. In particular, this is kind of flipped. So many neighbors mean a simple model, as we saw above here. So here, considering many neighbors makes it very smooth, basically. So many neighbors is more underfitting. So this curve is kind of mirrored compared to the curve above. Okay. So one more thing about parameter tuning, or and notebook 7, and then we're actually going to talk about models. So yeah, open notebook 7. So now I want to talk about how to adjust parameters. So here in this we saw what is the effect of parameters, but how do I actually choose the parameters, and how do I make prediction using the parameters? And so the way I like to do it is I split my data up into a training and a test set, and then to find my parameters, I do cross-validation on the training set the parameters, and then evaluate the parameters I found on a test set. What you can also do is go a little bit more nuts and do cross-validation in the outer loop, and find parameters for each split of cross-validation, and then test on the whole out set, what we call nested cross-validation. So it's important that you don't use the same set to find parameters that you use to evaluate your model. Because if you try out a lot of different parameter values, you might just get lucky in finding a good set of parameters that wouldn't actually generalize to new data. So it's important to keep like a separate test set to validate that the parameters you found actually make sense. And that's why I kind of split off some tests at the beginning and use it in the end to validate my model. So the way we usually find the parameters in at least in machine learning, is to basically we try out all possible combinations of the important parameters. We pick some range and then we try all possible combinations. If we have many parameters, that's a problem, but so it's live. And then we do cross-validation for each setting of the parameters. The way we do this in Scikit-Learn is using a class called GridSearch-CV. GridSearch-CV implements cross-validated grid search. As I said, I split off a test set in the beginning, so you can use it for evaluating later. I need to define the parameters and the grid I'm searching over. Here I'm using something that has two parameters. It's the SVC, which I'll explain later. And so this has two important parameters. And C and gamma, they both somewhat control how complex the model is. Small means simple model, and large means complex model. And I define as a dictionary where the keys are the parameters I want to search over, and the values are the values I want to try. And what grid search is going to do, it will try all possible combinations of things in the one list with things in the other list. Then I built my grid search here. So I instantiate this grid search CV object with SVC, which is the classifier I want to use, and the parameter grid. And now this grid search object that I built here behaves just like a normal classifier. So for example, I can call fit on it to build a model. What now happens behind the scene is it does threefold cross-validation. And using the threefold cross-validation, it evaluates all possible combinations of the parameters. So here you can see that it starts with gamma equal to e to the minus 5 and c equal to 0, 0, 1. And then it does threefold cross-validation. Next setting of gamma, same setting of c, and so on, and tries all possible combinations. After it finished trying all possible combinations, it picks the one that has the highest cross-validation score. Then it trains the model again on the whole training set using the best cross-validation score, or the parameters found by the best cross-validation score. And then it stores the model. And if you call predict, so this was a digits data set, so that's like you get digits from 0 to 9. If you call predict, it'll use the model with the best parameters that are found, trained on the whole training set. So this grid search now looks like that's the same as the classifier would, just it uses the best parameters. And you can call the score function. It does very, very well. You can look at what the best parameters are that are found. What do these tell you? Okay, they don't tell me that much, actually. So the more parameters you have, the harder it is to interpret. And so here, the model also stores in grid scores the scores for all of the possible combinations of parameters. And so I get out the mean validation score here, and then I plot it. So here I get the cross-validation scores for all the combinations of C and gamma. And because there's only two parameters, I can easily plot it. If I have more parameters, then this even gets harder. OK, so the thing I mentioned before, so you can do nested cross-validation by just using cross-val score to evaluate, like cross-val score on grid search CV. So here, I pass it the classifier, the parameter grid, the whole data set. This is like the whole data and the whole target's y. And I call cross-val score on that. So what this will do, it'll split your data into 3 parts because threefold cross-validation is the default. Then for one split of the data, it'll find the best parameters for this split and evaluate on the holdout split. Then there's a second split, find the best parameter using cross-validation, and so on. So this does like a lot of work, but it gives you a pretty robust estimate of how well you can do if you search over the parameters. OK, so what I want you to do is use grid search CV to adjust the number of neighbors in the k-nearest neighbor classifier on a digits data set. And then, so split your data set into training and test set, do grid search on a training set, and then see how well you can do on the test set. Huh? What? The error message is
Talk about k-nearest neighbor.
One nearest neighbor
What?
is the first nearest neighbor who is not me, not me.
I'm not my own.
No.
My own neighbors, but it's a
No, it's-
definition.
Yeah.
In
It depends.
When you talk about first nearest neighbor, you talk
Yes.
about in neighbor, the other one.
Yes, but if you build a class,
So long
yes.
as it's clear, so long as it's clear in the document. But so for the digits data set, any number of nearest neighbors don't tell me anything about what I am, because the nearest neighbors to me, the nearest neighbors here are the nearest neighbors given a metric or just in the data as is.
There's always a metric.
Okay.
Implicitly, I think by default it's always Euclidean.
Yeah.
It's obviously the best metric.
Well, which in this case means
on the
the
pixels.
third nearest neighbor to me is
She's very upset.
the
You're pretty good.
nearest neighbors are the nearest objects to me, right? So I have a 3, a 6, a 2, and a 1.
Yeah.
The nearest neighbors to the 3, 6, 2, 1, 3, 6 are 3 and 2. The 3 nearest neighbors, is that correct?
You're not talking about images though, you're just talking about numbers on a line?
Well, I'm talking about the digits data set.
Okay.
Right,
So what it's going to do is take the image, stretch it out as a vector of pixel values, and then do Euclidean distance on those vectors.
Okay.
Why?
Because I like straight font for transpose.
Oh.
I hate it when people use /top. Math SF?
SF? No.
Yeah, like that. No, Math SF curly brace. That looks nice.
Oh no, this is here. Wait, alpha. Is my math correct? Maybe I need eyes. Damn it. What? How do I make it below the min? How do I make... I need to do... How does it declare math operator? Do I have to declare math operator to make the W below the min?
Math yes.
I don't like it. Okay. Oh. And the bias.
I'm not quite sure because I know what that often with linear model, but the penalty term is the square.
Yes. Right. Otherwise, the derivative would have 1 over the square root in it. This way you get weight decay.
Okay.
So the derivative of this is just W.
Yeah. Okay.
Alright, but it makes... I got the same thing.
Yeah, I think actually that's true.
You're sure you shaped it the wrong way?
Sorry? Did I do the x and y axis wrong?
Yes.
Okay.
No, you try to do 20, 14. But it's like, I mean, you only searched over one parameter.
No, I was already changing two parameters.
Ah, you were
changing the leaf size and the neighbors.
Ah.
So
Wait, can you show?
So my parameters are the neighbors and leaf size.
And what? K neighbors classify? Ah, leaf size is just an optimization, so it'll actually not change the outcome.
Oh, okay. Wow.
So that's, but you can see that in the plot, right?
Yeah, the fact that it's just constant over leaf size. Okay. No.
It's a heuristic to speed up the processing. Now I'm going to do linear models. Finally. I should have explained nearest neighbors at the beginning.
Yeah.
It would have been better. Yeah, yesterday I was all day at Strata, and I was preparing Strata stuff on the weekend, so I didn't have that much time to prepare this. And I was hoping the nearest neighbor were clear from the plot I showed above, but it wasn't, and I should have explained it better. Yeah, next time. So one out with a German ASUS thing. Or European ASUS?
Yes.
I have the same.
In Germany, you have specific plugs too? It's not European?
No, it's a European one.
Yeah, this is European.
Yeah.
But it's actually South Africa, but it is South Africa.
Okay.
So I said parameter and put it into research and calculate that.
Oh, it looks like there's a space after end neighbors.
Yes.
Oh, you have a space there.
There's food. Is that lunch?
Yeah, all we get is crisps.
Well, in this country, crisps classify as a side dish, right? So.
Well, but if the students see there's no one in here.
Yeah, and the previous one was 0.
Any burst, there is no check that it's 0. It just crash. If any burst is...
And then it's fixed in master.
Ah, okay.
Or maybe it's fixed in 16 too.
Ah, because she was still me.
So in this case, a grid kind of makes sense because n neighbors is discrete. But in the previous case with C, I mean, wouldn't you like it to actually just fit that function and trying to find the maximum rather than the grid that you give it?
Well, usually it's easier to use a grid. You can use Bayesian optimization methods to try to fit this function and optimize it at the same time. That works well if you have a lot of parameters and your model is very expensive. Sometimes it's just better if you have many parameters to randomly sample instead of trying to do Bayesian optimization from some continuous distribution. I mean, the function that is not necessarily convex, so optimizing it and fitting it is like non-trivial.
Then we'll go back to 10.
It worked, right? It's just waiting for the couple seconds.
Whose iPhone on the floor?
Mine, probably.
Running score. Okay.
I'm going to go back and do it.
Yeah, each one of them. Definitely bad if you have 6
So who's ready to learn something about the actual models? Okay, 2 people. 3 people. From this one?
I had thought that from the last thing we did, I thought that one nearest neighbor was the best. Everything else was fitting over.
Well, here it looks like 3 nearest neighbors is the best. It also, it depends, because this data set is small, it depends a bit on the random state for the training test split, because the train test split does a randomized split of the data set, and depending how that goes, slightly different values might be best.
And then in the grid search it says 1 nearest neighbor is the best.
When I ran mine again, it said 3.
Well, so maybe there's not much difference between 1 and 3, and so let's see how the... I mean, you can see here that there's pretty wide uncertainty here. So, and I mean, this kink here also looks kind of suspicious to me. So maybe this is kind of pretty noisy estimate. So it's kind of unclear whether it should be 1 or 2 or 3 or 4. The main takeaway was how to search over multiple parameters and then apply it to an unseen test set. So it's important that you have like a separate test set that you didn't use to tune the parameters. So now I want to go to 9.1, which talks about linear models. So we're going to skip 8 for now. Yeah? How does it decide what's best? Well, it uses a score function. By default, it's accuracy, but you can give it any other score function. And it applies this using cross-validation. So you do cross-validation with each set of parameters, evaluate using this given score function, and the one that's is highest is the best.
So it's just completeness. Like it doesn't.
It's accuracy.
You cared more about like the number of. I don't know. Can you adjust like what the best is?
Yes, you can give like other scoring metrics, and you can actually give a callable and give it an arbitrary function. Is completeness the same as accuracy?
Recall.
Yeah, completeness is recall, right? Accuracy is how many are correct. Okay, so now I want to talk about linear models for regression. So regression is when you have like a continuous output variable, and you all said you know how linear regression works. So basically, you make a new prediction as for each feature, you learn some coefficients, and then you do the inner product. And these coefficients are sometimes called weights. In Scikit-Learn, they're called coef underscore. And then there's an intercept, which is like an offset or bias term, and it's called intercept underscore. And so you make a prediction just as a linear combination. That's true for all linear models, not only linear regression. But there's different ways to learn these coefficient parameters and the intercept. That's what I want to go over. So here I make a regression data set that's like a synthetic data set that has 80 samples, 30 features, and only 10 of these features are important. So this is like a synthetic noisy data set that actually has like a linear relationship between the data and the output y. And there's some known true coefficients and some added Gaussian noise. And so I split it into a training and a test set, and I have now a training set with 60 data points described by 30 features. And I can now do a linear regression on this. So linear regression, so I just added the formulas so you don't have them, sorry. And hopefully I did the formulas right. We just want to find the parameters, the w and b, so the coefficients and the intercept that predict y best in a least square sense. So we use the L2 distance to measure how good we are, and we try to find w and b we try to find w and b or coef and intercept to minimize this. So here xi is one data point, yi is that's the label, and I sum over all the data points I use in training. But you said you all knew that, so that's good. So in here, I import from linear model. I import linear regression. I fit it on a training set, and I score it on the training set and on the test set. And so it does pretty well on the training set. So I use the r squared, which is coefficient of determination, I guess. And that's 0 is random correlation. Basically, 1 is perfect. And so on a training set, we're quite good with 0.87. But on a test set, we're quite below that at like 0.5. So the score function on regression models is this r squared score. We could also use mean squared error if you want to. And so what does this tell us? Yeah, it's a big discrepancy between how we perform on a training set and on a test set. No? This tells us we are overfitting. We fit a too complex model. It does well in the training set, but it doesn't generalize. So we need to make our model more simple. Actually, before we do that, I want to go into a bit more detail of what this model is. So I want to compare, as this is synthetic data, we know the true coefficients. And so this is, we can compute the model, the linear prediction, using the true coefficients. And we can compute how well we would do if we knew the truth. And actually, if we knew the truth, we can get like a score of 0.73. So there's only that much information. The rest is noise. And so this is the best we can hope for to be on to generalize with like a r squared of 0.72.
Well, that should be your goal for the training set. That should essentially be your target for the training set.
Yes. If you do better on a training set, you are overfitting, basically, yeah. But obviously, in real life, you don't know what that is, because it uses the true model that we know because we create a data set, but you never, if you knew that, you were done. And here, I plot the coefficients. So there are 30 features. So I have 30 coefficients that tell me how important each feature is, or like what's the coefficient. And they're so in blue I plotted the true ones. I sorted by the magnitude of the true coefficients. So the on the very left are the large ones, the important ones, and then it goes to right. And the last 20 ones are 0, so they don't matter at all. And you can see that the linear regression well, maybe kind of matches some of them. But you can definitely see that a lot of them that are unimportant have quite large coefficients, and so I mean, maybe some of them got recovered, I don't know, but it doesn't seem to be very close to the truth. So one way to make a linear model more simple is to do rich regression, which means to add an L2 penalty. What it says is we try to minimize our parameters W and B, not only so that we fit the training data well, that we are close to our output Y in the least square sense, but also that the magnitude of this W is small. So basically we want to make two coefficients more or less be close to 0. So we want to keep them small. And if we keep them small, that kind of forces the model to be more simple. So what I do now is, and how much we force the model to be small is this parameter alpha, which is like the model complexity parameter that you would search over here. So I try 4 different values of alpha in a rich regression. And for each one, I fit the model, and I compute the training and the test score. And then I store the model. And then I forgot to plot.
Sorry, high alpha is low complexity. Which way does it go? High alpha is low complexity.
High alpha is high regularization, because high alpha gives the second term more importance. So you want to shrink W more. It's the other way around than C, which is totally not confusing. So, and here actually, yeah, you see the way I plotted it. Here's our high values, here are low values. So this plot maybe reminds you of the plots we saw before, that for high values of alpha you're underfitting. For like the mid-range there's like a sweet spot at 10, and for very low values of alpha we are overfitting. Okay, so this looks kind of familiar. And we can also plot the coefficients. So here I plot the true coefficients in blue, and then sort of going from blue to yellow. So yellow is very little regularization, and the green is a lot of regularization. And you can, so we're making the model very simple. And you can see that sort of the yellow one is always furthest out, and then sort of the darker you get, the more you get to 0. And you can see that so maybe the second one was kind of best, the 10. 10 is like this dark green, and this is kind of reasonable in a lot of places, but you see that some of the coefficients are pushed a lot to 0, because the model tries to make all the coefficients very close to 0. But some of them that are not important are still non-zero. So, but that's a very common way to like penalize the model. And so if you make alpha very small, you basically recover the linear regression, because if alpha is very small, this term goes away, and you only have the fitting term, and you have linear regression. There's another model that's popular, which is called the lasso, which is an L1 penalty. So you have in the front you have the model fitting term, but you also have a term that says you want W to be small in an L1 sense. So this is L1 norm is just the sum of the absolute values. So intuitively, maybe that also means shrinking everything to 0, and that's what it does. But for some slightly non-trivial reasons, it actually enforces some of the coefficients to be exactly equal to 0. So it will mean that it'll find some coefficients that it thinks are not important and set them exactly to 0. Again, you have this parameter alpha that says how much you want to force things towards 0. And again, I forgot to plot. And again, you get a similar curve. Let's compare. So I think this is actually, so here this is like 58 as the highest point. And here it's like 60. Well, it's slightly better. But the main difference is in, if you look at the coefficients, you can see that if we have like an alpha of 10, then a lot of the coefficients are exactly 0 here. So if you don't see the blue dot, it means like a green dot is above it. So a lot of the coefficients are set exactly to 0. If you make the alpha too high, it'll set too many of them to 0. So for example, this one are at some point also set to 0, even though they were important in a true model. Okay, so these are like two very helpful models for doing regression. So, basically, if you think, I mean, these two models, they are sort of different prior assumption about the model. If you think only few features will be important, you should use the lasso. And if you think like, if you don't know if maybe all of your features might be important, then you should use the ridge. But you should never use the linear regression. Maybe. So now I want to talk a little bit about linear models for classification. I didn't write down the loss function for this, so they're slightly more tricky, but not much more tricky. The model fitting part is a bit harder, but the predictions are made in the same way. So you just do an inner product between the features and the coefficients, and you add some intercept, and then you ask, is the thing that I get out greater than 0 or not? If it's greater than 0, I predict +1. If it's smaller than 0, I predict -1. So that's for two-class classification. And bye, Brian. There's another way. So actually, so linear models for classification are the linear SVC and logistic regression. They are very, very similar. And so they both find a linear function and then threshold it. And the regularization here, the C parameter, does exactly the same, or the inverse of what alpha does. So it shrinks the coefficients towards 0. But it also has some slightly different interpretation. You can see here, we're trying to classify these blue points at the top versus the red points at the bottom. And I used the linear SVC to find the separation. So here there's this black line is the separation that the linear SVC found. On the left-hand side, I have a small c, so that's a very simple model. And you can see that it's basically horizontal, which means it is more oriented towards like where the majority of the points are. So the majority of the blue points are at the top, the majority of the red points are at the bottom. So we get like a very horizontal line. If we allow ourselves a more complex model, if you go to the right, larger C, more complex model, then each individual data point will become more complex, will become more important. And so you get more and more points correctly. So you bend more and more, and then you get this red point at the top. But this might not sort of, but now you have something that is very attuned to the single data point, so you might be overfitting. But this is like, this difference is done just by changing the magnitude of the coefficients, which is slightly not obvious. So this is for binary classification. You can also do multi-class classification. And I'll briefly show this here. So here, sorry. I make this 3-class data set of blobs in 2D. So again, one feature on the x-axis, one feature on the y-axis. And so you want to separate these 3 classes with a linear model. And the way the linear model does that is it builds 3 different models. one model is to separate the green from the other two, one to separate the red from the other two, and one to separate the blue from the other two. So each class basically gets its own model. This is called one versus rest. And a lot of the machine learning models work like this. And you can see that, so here I've used a linear SVC, and I fit the model on x and y. The shape of the coefficients is 3 times 2. It's, so 2 is the number of features here, the x and the y axis in the plot, and 3 is the number of classes. So each class has its own coefficient vector. And each class has its own intercept or offset. And I can plot the lines that are given by the coefficients, and these are the 3 lines. So there's one line to separate the green from the rest, one to separate the red from the rest, and one to separate the blue from the rest. And that's how you do multi-class linear classification. So I mean, maybe we need not to do the first one, but we can do the second one. So you can change the penalty in the SVC between L1 penalty and L2 penalty. So basically, these correspond to the rich kind and to the lasso kind. And then you can plot the coefficients on the digits data set. And so you can do that. You should change the data set to classify odd digits versus even digits, so you have a binary task. Because in a multi-class task, you will have many more coefficients that would be kind of nasty. So make the target whether the data point is odd or even. So that's just just this, and use this and train a classifier on predicting whether a digit is odd or even, and then train a linear SVC with L1 penalty, visualize the coefficients, train it with L2 penalty, and visualize the coefficients.
So in the previous plot, there is a test sample that goes right in the middle. The middle triangle, the classifier will say it's not the
No, so usually it'll pick a random one. I mean, it would be better to say none of the 3, but that's usually not. So actually, it'll take the minimum distance to the hyperplane. So if it's exactly in the middle, it'll take a random one. Usually in machine learning, you don't allow yourself to say none of the above. I mean, it's usually not, depends on how you define your task. I mean, sometimes you allow yourself to do that, but it makes evaluation harder. But it would, if you're in the middle, it would do the closest line.
Why is 1 the default value? Like, it's presumably it's scaled such that 1 the default value is a good match, but what is it scaled?
1 over number of samples. So C is number of samples by alpha in the formulations above. At least for the rich. For the lasso, no. For the rich, it's just alpha. Nah, wait. Okay, so it's scaled by the number of samples in the penalty. So it's the penalty is C divided by number of samples divided by C. Yeah. And 1 works well.
I'm just trying to wrap my head around like what types of problems you would apply this to. So are you saying that you're taking your data points and the thing that it's mapping to is a non-discrete classification system, and you're assuming that you're using a linear model to do that?
What do you mean by non-disc? So in the regression, it's.
I guess I'm talking about like the very beginning.
Okay, so that's like you want to predict a continuous quantity.
Yeah.
Um,
I'm thinking of Y as like a classification scheme, but.
No, so here you shouldn't. Sorry, you shouldn't think about it as a classification scheme.
Yeah, exactly. So you're taking a bunch of data points and you're mapping them to a non-discrete value.
Yes. Did you raise your hand when I asked you if you know what linear regression is?
Yes.
Okay. Yeah. No. Why is it continuous?
Well, yeah, duh. But I'm just saying, like, what types of things would you?
Okay. Yeah, you can predict salary. I don't know what your continuous tasks are. The size or weight of some astronomical object.
No,
or
I was just making sure I understood. What
yeah. No, that's like.
What the Y value is.
Yeah. So any continuous quantity.
So are the linear classification model in SVC basically?
There's SVC is one type of linear classification model. Linear classification models are all that make a prediction of this form. Like you do some linear weighting of your features and then you threshold. That's the definition of making a linear classifier. The SVC is one particular way to find the coefficients. Logistic regression is a different way to find the coefficients. Sorry?
That's not very used.
What's not very commonly used?
Because what you have on the right hand is some continuous value. That goes.
Sorry, you threshold the continuous value at 0. Why do you think it's not useful?
I don't know, like it's more natural to have logistic regression. I don't think.
Logistic regression does that.
But then you need a function on the right part.
No. For binary logistic regression, you just take. You map it to a probability and you threshold the probability as 0.5, but it's the same as thresholding the output that you get at 0. If you compute the coefficients in your logistic regression and you do that, that's the output it does. We're just not making I didn't say we're making a probabilistic estimate here.
Are you going to talk about probabilistic estimates?
No, that's Friday. There's a function predict proba that gives you a probabilistic estimate for some models. It may be good or bad. You don't believe me, right? So, you do. This is like the decision rule for logistic regression, right? You do Wx and you do sigmoid, which is like 1 over 1 plus x of minus Wx, something like that. But saying this is greater than 0.5 is the same as saying Wx is greater than 0. Because,
Yeah, but the probabilistic looks like linear regression there. So
Sorry?
it looks like linear regression there.
Yeah.
So that's why it's fascinating.
But linear, because I didn't write down the loss. But to make a decision in logistic regression, you don't never ever need to compute the exp.
But you don't always use 0.5.
Yes, that's true. But for example, this linear SVC doesn't give you a probabilistic estimate. Okay, then I'm gonna do one more notebook, or should I stop now?
Depends how hungry people are. How their hungriness and correlate with their...
Okay, so there's gonna be a decision to make. Either we're gonna talk about trees and forests, or we're gonna have lunch. So who wants to have lunch? Okay. Okay, yeah, sure. We're gonna do this exercise now. It means people didn't like it.
So I can get back there and unwrap it before everyone is back. Just give me 5 minutes to take yourself off before you start.
Try taking yourself out of your pocket.
Sorry?
Take yourself out and interfering with the... Or someone thinks that on Twitter.
Was it recently?
Oh.
Sorry, I bet you saw it.
I can't see it
Okay.
People hitting the wall.
Yeah.
The thing with linear regression is, it occurs to me that probably relatively few of us actually work on this stuff. So it could be that people have heard of linear regression and think they know how it works, but maybe not so familiar with it that they can go along.
Yeah.
So that might.
That was not a.
Some of the
Yeah, that I might have explained it. Should have explained it probably in more detail, but.
One thing was that
Yeah, I should have started with explaining some of the models. Didn't have time to redo all my material yesterday.
No, it's tricky, but we have time to.
Yeah.
Then unless you want people